Here we are. We're trying to find the current that's going through this battery. Let's begin. Alright, what do we know? We know a couple of things. One, we know the change in voltage across the resistor is equal to the current times the resistance. We also know that the total resistance of resistors in parallel, or rather the inverse of that, is equal to the sum of the inverses of the resistors in parallel, etc. We're only going to deal with two though. We also know, much simpler, that resistors in series are just the sum of the resistors. So let's do what we can for now, and we may need to use something else. Alright, so what do we have to do here? First thing we should look at is this resistor in parallel. We got a 2 ohm resistor and a 6 ohm resistor. So the sum of the resistances is going to be this plus this. And then we can simplify this. That means that's going to be 3/6 plus 1/6, that's 4/6. So 1 over 4/6 is going to be 6 over 4. So get rid of all this. I hope you trust me on that. Get rid of this. This is going to be 6 over 4, so that's 1.5 ohms. And you guys can figure out pretty quickly, 2 ohms plus 1.5 ohms is going to be 3.5 ohms. So you can make that. Alright, so let's move on. We've solved this. Now we need to solve these resistors. So where do we begin? It's really not clear, is it? I guess the problem is we can't identify which resistors are in series and which resistors are in parallel, because it's sort of a jumble. These are in parallel, but they're also in series with this, and really nothing is clear. So what we have so far isn't going to get us anywhere. We're going to have to introduce Kirchhoff's laws. This first law is that the current in to a junction is equivalent to the current going out of a junction. So that's obvious for any two-way junction, such as this, because it's the same piece of wire. It's hardly even a junction, really. But it's very easy to see that the current going into this is going to be the current going out. You don't need that explained to you. Now, it's a little more complex, but still relatively intuitive here. The current, and thus the charge, because current is charge per second, going into this junction is coming from these two sides. I'm assuming that right now. And it's been coming out like this. So if this current is not equal to the sum of these two currents, then that means the charge coming out of here is either less than or greater than this charge. If it's greater than that, then we have charge coming from nowhere. That's impossible. And if it's less than that, then we're going to have charge building at the junction, and it's going to build infinitely. We're going to have big problems, and basically that's not possible. So we know that In equals I out. So that means we can write a number of equations. We're going to have to label some currents. So I'm going to draw a couple of lines, and there's no real way of knowing which way the current is going to be going here. So let's just say for now it's going to be this. If it's not going to be a problem. We just have to we just need to assume that this is the case and stay fixed there, and we're going to have those go like that. So this is going to be 1, 2, 3, 4, and 5. So we know that according to I in, I out, we know that, we'll call this I naught. We know that I naught equals I1 plus I2. We know that I1 plus I3 equals I4. We know that I2 equals I3 plus I5. And we know that I4 plus I5 is going to equal the current going through the battery, which we're just going to call that big I, because that's what we're trying to solve for. Unfortunately, this doesn't do us a lot of good because we don't know any of those currents, so we're going to need to use Kirchhoff's second law. Now here is Kirchhoff's second law. The change in voltage around any loop is equal to 0. So this is a bit more complex than the last one, but I can explain it pretty easily, giving you a couple equipotential lines. So at any point on here, on this circle, they're all going to be at the same potential. And we know, from what we know about voltage, that this can travel around any path it wants to, any path at all. And if it winds up back in this line, the net work done on it will be 0. So that means that any point on the wire, if it moves around, goes however it goes, and gets back here, since it's in the same place, no work can have been done on it, which means it can't have passed through a change in voltage. So, using Kirchhoff's two laws, we're going to find a system of equations that can help us solve everything and eventually the current through here. We'll start with a basic example from this circuit. Start at this point. We're going to go around this loop and come back to here. So 0 is going to be the net voltage around the loop. We go up from the negative end to the positive end of the battery. That's going to be 5 volts. Around here, down, the current is going with the way we're going, which means we're going to subtract. So minus 2I7, which is, we know that from V equals IR. And then we come back and we're here. So I7, we know 2I7 equals 5, which means I7 equals 5 over 2. So now that you've done one easy example, remember that I7 equals 2.5, we're ready for some big boy stuff. We're going to start a loop here and go around. So, we know that total voltage is going to be 0. We can go up negative end to positive end of the battery, 20 ohms, minus 3.5 big I. Down here, that's going to be minus 2I7. We go through here. Let's take the simplest path we can for now. So, minus 2I1 and minus 5I4. When we get back to our same location. So that's definitely not going to be enough still to solve this whole circuit. Keep in mind, however many variables you're going to have to solve the system of equations, you're going to need that many equations. And you can look at any circuit really and know whether or not you're going to be able to solve it. And we know because we have all the resistors and all the batteries, we're going to be able to solve this. So we could continue, but we know that because we have everything, that we could build a system of equations using all the possible loops, so going through here, etc., that we would have enough equations to enter into a matrix that could solve for all our currents. I'm not going to do that, but we will show you how to in part 2. For now, we're going to move on to RC circuits. Here's another useful application of Kirchhoff's second law. We're going to solve a circuit that has a capacitor and a resistor in series. We have a battery of known EMF E, capacitor of known capacitance C, and resistor of known resistance R. We know that Q equals CV, that's the equation for a capacitor, and we're going to need the change in voltage across it. So V equals Q over C. So we're going to start from this point here. The total voltage is going to be 0 plus the EMF minus change voltage, which is going to be Q over C, capacitor minus IR. Where we can go from here, though we're not going to solve it, so we can make a differential equation because we know that I equals dQ dt. So we know that 0 equals E minus Q over C minus dQ dt times R. Using this, we can set up a differential equation and solve